Watch this commercial jet engine turbine spinning up. While it provides the thrust necessary for flight, it also serves as the primary source for a massive electrical grid. A single engine-driven generator on a transport category aircraft produces up to 110 kilovolt amps of power. Reliability at 40,000 feet is maintained through an automated dynamic network topology. This architecture is designed to actively monitor and reroute the power it generates. Engineers assume that physical parts will fail. Severe anomalies, from major short circuits to the total mechanical loss of an engine, are expected variables. The electrical network is specifically mapped to absorb and route around these failures in real time. To understand how aircraft avoid catastrophic blackouts, we have to look at the avionics that manage this power flow, the specific bus topologies used to isolate electrical faults, and the strict energy hierarchy that takes over when primary systems go offline. Before we break down the network, subscribe to Insight Engine and like this video to support more professional-grade technical analysis. Total electrical blackouts are virtually impossible by design. Aviation architecture achieves this through redundant pathways and independent logic controllers, creating a system that routes around damage before the crew is even aware of a fault. Heavy transport aircraft operate on a baseline standard of three-phase alternating current, running at exactly 115 volts and 400 hertz. Holding that electrical output steady is an immense computational task. This is handled by a dedicated computer called the Generator Control Unit, or GCU. Its primary job is strict regulation, maintaining that exact voltage and 400 hertz frequency regardless of what the engine is doing. Watch this GCU process raw output. Engine RPM fluctuations create erratic waves. The GCU forces this chaotic input into a perfectly uniform sine wave. Acting as gatekeeper, it commands the generator breaker to close only when parameters are perfect, allowing safe power into the system. Once the power is on the grid, a second tactical computer takes over, the Bus Power Control Unit, or BPCU. While the GCU creates the power, the BPCU decides exactly where it goes. To distribute current effectively, the BPCU needs to know exactly how much power is flowing through any given section of the aircraft at any given millisecond. It feels the network load using sensors called current transformers. Here is a current transformer ring on a main cable. Alternating current induces a smaller voltage, streaming raw data to the BPCU. The BPCU processes this instantly, commanding heavy-duty bus tie breakers to dynamically snap open or closed, distributing the electrical load where demand dictates. Human pilots cannot monitor fluctuating voltages, calculate load balancing, and mechanically throw switches fast enough to prevent an overload. Delegating this entire process to automated control units is a hard requirement to keep the network stable. In modern twin-engine aircraft like the Airbus A320 or Boeing 737, the BPCU operates within a specific architecture known as a split bus topology. A split bus system operates under one strict rule. The left engine generator and the right engine generator feed entirely separate distribution buses, and they must never power the same bus simultaneously. This visual shows why. The output current between two independent generators is not phase regulated. If you connect two out-of-phase AC generators to the same line, their waveforms collide. The resulting voltage spike would destroy sensitive avionics instantly. Beyond keeping generators separated, the topology must also survive localized physical damage, like a bare wire grounding out against the airframe and causing a massive short circuit. The first line of defense against a dead short is a physical component called a current limiter. These are not the small, resettable circuit breakers you find in the cockpit. Current limiters are high amperage components, often rated for 325 amps or more, designed to completely melt down and sacrifice themselves to sever a dead connection. While a pilot can easily reset a tripped breaker in flight, a blown current limiter means the physical bridge between buses is permanently destroyed until a technician replaces it on the ground. If a short circuit flashes across a subbus, the system reacts in milliseconds. The BPCU detects the massive spike and fires the adjacent bus tie breaker open. That subbus drops offline, but the rest of the electrical grid reroutes around the dead zone, operating normally. When catastrophic, localized damage occurs inside an electrical grid, physical isolation is vastly superior to synchronization. By cutting off the infected branch, the core system survives. Larger aircraft require a different approach. A Boeing 747-400 utilizes a parallel split architecture to handle its massive electrical demands. With 4 engine-driven generators, plus an auxiliary power unit in the tail, the routing logic here is intensely complex. In this schematic, all 4 generators actively share the load. If generator 1 fails, the system instantly splits and dynamically reroutes power from the remaining engines. To ensure critical components stay powered, dual-feed buses receive redundant power lines from entirely different sides of the network. Connecting 2 main networks to a single node creates a vulnerability. If a fault occurs, destructive energy could travel backward, taking out the backup generator. The solution is a reverse polarity diode. It acts as a one-way valve, blocking rogue current from surging backward. This abstract wiring logic dictates practical flight safety. Engineers deliberately distribute high-draw, mission-critical thermal loads across these heavily isolated subnetworks. Take windshield heating. The heating elements in the pilot's windshield are wired to an entirely different electrical bus than the elements in the co-pilot's windshield. If a major short circuit destroys the left side heating bus, the right side bus remains fully powered. The aircraft retains forward visibility, preventing a localized electrical failure from escalating into a fatal icing hazard. There is an ultimate nightmare scenario: fuel starvation, volcanic ash, or a dual-engine flameout causes the simultaneous mid-flight loss of all main AC generators. The first automated response is to start the auxiliary power unit, a small turbine in the tail that can spin up and assume the AC electrical load to keep the flight displays and hydraulics alive. If the APU fails, the aircraft deploys the ram air turbine, or RAT. This small mechanical propeller drops from the belly of the plane, using the rushing airflow to spin a backup generator and buy the crew crucial time. If every single engine, turbine, and AC generator stops spinning, the aircraft relies on its absolute final barrier against a total blackout, the onboard battery and the direct current system. This brings us to the single most critical node in the entire airframe, the hot battery bus. In this simplified DC schematic, the AC grid is dead. The battery wires directly to the hot battery bus, bypassing all relays to remain permanently energized. This node powers absolute survival equipment only: engine fire extinguishers, main fuel shutoffs, and emergency radios. To power the digital flight displays, the DC power from the battery runs through a static inverter, a solid-state component that transforms the direct current back into 26-volt and 115-volt AC power. This produces a highly restricted trickle of electricity. It is precisely calculated to keep only the captain's primary flight instrument and the standby attitude indicator alive, providing just enough spatial awareness to execute a dead-stick emergency landing. System resilience in aviation relies on accepting that components will break. Engineers build an architecture with a topology designed to instantly diagnose a fault, isolate the damage, and sever its own electronic limbs to guarantee the survival of the core.